Questions are beginning to ripple through the global earthquake monitoring community as an extraordinary burst of seismic activity unfolds along one of Earth's most dynamic plate boundaries. Why has a normally active corner of the Southwest Pacific suddenly produced so many moderate earthquakes within such a brief span of time? Does an accelerating swarm signal that enormous stresses are being redistributed deep beneath the ocean floor? Or is it simply another reminder that the Tonga Trench rarely remains quiet for long? Every fresh seismic alert adds another piece to a geological puzzle that scientists have spent decades trying to understand. Yet even with modern monitoring technology, the answers remain remarkably complex. During the past several hours, the southern section of the Tonga Trench has experienced an intense earthquake swarm, featuring multiple magnitude 5+ earthquakes accompanied by numerous magnitude 4+ events. According to data released by the United States Geological Survey, at least 11 earthquakes reaching the upper magnitude 4 and lower magnitude 5 range struck the same offshore region in rapid succession. Several registered approximately magnitude 5.2, while others measured magnitude 5.1, magnitude 5.0, and magnitude 4.9. Although each individual earthquake falls well below the threshold of the world's largest seismic disasters, their close spacing in both time and location has immediately drawn attention from researchers who monitor tectonic activity throughout the Pacific Ring of Fire. Unlike isolated earthquakes that release accumulated stress during a single rupture, a swarm represents an extended period of repeated fault movement across a confined area. Instead of one dominant main shock followed by progressively weaker aftershocks, earthquake swarms often consist of many events of similar magnitude occurring over hours, days, or even weeks. In tectonically active regions, these sequences can reflect changing stress conditions as neighboring faults respond to one another, redistributing strain through an interconnected network beneath the Earth's surface. Few places illustrate this process more dramatically than the Tonga Trench. Stretching for approximately 1,000 miles, or more than 1,600 kilometers, across the Southwest Pacific Ocean, the trench marks the boundary where the massive Pacific Plate dives beneath the smaller Australian Plate. Far below the ocean's surface, this relentless collision generates some of the deepest earthquakes ever recorded while simultaneously fueling one of the planet's fastest-moving subduction systems. The remarkable speed of this convergence is what makes Tonga exceptional, even among the world's major subduction zones. Along portions of the trench, the Pacific Plate descends beneath the Australian Plate at rates approaching approximately 3½ inches every year, or nearly 90 millimeters annually. Elsewhere along the trench, convergence commonly exceeds approximately 3 inches, or roughly 85 millimeters each year, before gradually decreasing toward the Hikurangi margin near New Zealand. By comparison, many famous subduction zones around the world move at substantially slower rates. The Cascadia subduction zone beneath the Pacific Northwest advances only around 1½ inches, or approximately 40 millimeters, each year. Japan's Nankai Trough generally converges near 2 inches, or roughly 50 millimeters, annually, while many segments of the Chilean margin average somewhat higher, but still remain slower than the fastest portions of Tonga. Every year, those seemingly modest distances accumulate into enormous amounts of stored energy. Plates moving only a few inches annually may appear insignificant from a human perspective, yet over decades and centuries they transport entire mountain ranges worth of rock toward one another. Because the edges of tectonic plates rarely slide smoothly, friction locks portions of the boundary together while the surrounding crust continues moving. The result resembles a slowly bending spring that stores elastic energy until the rocks eventually fracture or suddenly slip. That continuous loading helps explain why the Tonga region experiences thousands of earthquakes every year. Many are too small for people to notice. Others occur at extraordinary depths extending hundreds of miles beneath the surface as the descending Pacific Plate sinks into the Earth's mantle. The subducting slab remains sufficiently cold and rigid to fracture even after reaching depths exceeding 400 miles, or more than 640 kilometers. Few places on Earth produce such an extensive vertical range of earthquakes. The geometry of the Tonga Trench also contributes to its extraordinary seismic productivity. Rather than descending at a shallow angle, the Pacific Plate bends sharply downward before plunging deep into the mantle. This steep configuration allows stresses to accumulate across multiple sections of the slab simultaneously. Some earthquakes originate directly along the plate boundary where the two tectonic plates remain in contact. Others occur within the descending Pacific Plate itself, as enormous compressional and tensional forces crack the sinking oceanic crust. Still others develop within the overriding Australian Plate, as stresses ripple upward through the surrounding rocks. This complexity means that an earthquake swarm can involve several different faulting mechanisms occurring almost simultaneously. Without detailed focal mechanism analyses, it is often impossible to determine immediately whether every earthquake represents motion on the megathrust interface itself or whether many originate within the subducting slab. That distinction matters because each mechanism reflects different stress conditions operating beneath the trench. Naturally, comparisons have already emerged with one of the most remarkable seismic sequences ever documented in the region. During the year 2021, the Tonga Kermadec subduction system experienced a spectacular progression of earthquakes that eventually culminated in a magnitude 8.1 megathrust earthquake. That sequence did not emerge without warning. Prior to the main shock, seismic activity increased noticeably across the region, eventually producing a powerful magnitude 7.44 shock shortly before the massive rupture occurred. The succession attracted worldwide attention because it demonstrated that great earthquakes can sometimes be preceded by escalating seismic unrest. Yet that history also illustrates why scientists remain cautious whenever a new swarm develops. The overwhelming majority of earthquake swarms in Tonga never progress into giant megathrust earthquakes. The region is among the most seismically active places anywhere on Earth, precisely because the plates are moving so rapidly. Frequent clusters of magnitude 4 and magnitude 5 earthquakes are therefore part of the natural behavior of this exceptionally energetic plate boundary. Although the current sequence deserves careful monitoring, a swarm by itself is not considered reliable evidence that another magnitude 8+ earthquake is imminent. For researchers, the real challenge lies in distinguishing ordinary seismic clustering from the extremely rare circumstances that precede a truly great rupture. That question becomes even more intriguing because every new earthquake slightly alters the stress field surrounding it, raising an important issue that continues to drive scientific research. When does an ordinary swarm remain just another episode of tectonic adjustment, and when does it become the opening chapter of something far larger? The distinction between an ordinary earthquake swarm and the beginning of a major seismic crisis depends on far more than simply counting earthquakes. Scientists examine a broad range of characteristics before drawing conclusions. They study whether the hypocenters are migrating along the fault, whether magnitudes are steadily increasing, whether focal mechanisms reveal consistent fault motion, whether nearby global positioning system stations detect unusual ground deformation, and whether the pattern departs significantly from the region's long-term seismic behavior. Only after assembling all of these pieces can researchers begin assessing whether a sequence is behaving unusually. Even then, forecasting the evolution of a swarm remains one of the greatest unsolved challenges in earthquake science. That uncertainty explains why seismologists consistently avoid making dramatic predictions after the first few earthquakes of a swarm. Every large earthquake begins with smaller ruptures somewhere, but almost every cluster of smaller earthquakes eventually fades without producing a catastrophic event. This statistical reality often surprises the public because hindsight creates the illusion that warning signs were obvious. In truth, the overwhelming majority of earthquake swarms simply represent the Earth's ongoing adjustment to constantly changing tectonic forces. The Tonga Trench provides one of the clearest demonstrations of this principle. The region experiences an extraordinary number of moderate earthquakes every year because it occupies a unique position within the Southwest Pacific tectonic system. The Pacific Plate does not merely slide beneath the Australian plate, it descends at remarkable speed, while simultaneously interacting with neighboring microplates, back-arc spreading centers, transform faults, and volcanic arcs. Each component continuously redistributes stress throughout the surrounding crust and upper mantle, creating an environment where earthquakes occur with exceptional frequency. Adding further complexity is the nearby Lau Bassin, located immediately west of the Tonga volcanic arc. Unlike many subduction zones where the overriding plate behaves as a relatively rigid block, the Lau Basin is actively stretching apart through a process known as back-arc spreading. As the Pacific Plate sinks rapidly into the mantle, it effectively pulls the overriding plate eastward, causing the crust behind the volcanic arc to thin and fracture. New oceanic crust forms within the basin while the subduction process continues simultaneously at the trench. This unusual combination of rapid convergence and active extension creates one of the most tectonically dynamic regions on the planet. Instead of stress accumulating within a single fault system, forces are distributed across multiple interacting structures. Compression dominates along the megathrust interface, while extension influences the back-arc basin. Transform faults accommodate sideways motion between crustal blocks, and volcanic systems respond to changing pressures deep beneath the surface. Together, they generate an intricate network of deformation, unlike almost anywhere else on Earth. Another remarkable characteristic of the Tonga subduction zone is the extraordinary depth reached by many earthquakes. While shallow earthquakes generally occur within approximately 43 miles or about 70 kilometers of the surface, Tonga routinely produces intermediate depth and deep focus earthquakes extending far beyond that range. Some events occur more than 400 miles, or roughly 660 kilometers below sea level, placing them among the deepest earthquakes ever recorded globally. Deep earthquakes remain one of geology's enduring mysteries, because rocks subjected to such immense temperatures and pressures should theoretically deform gradually rather than fracture suddenly. Yet the descending Pacific Plate remains sufficiently cold and mechanically strong to preserve brittle behavior long after entering the mantle. Scientists believe several mechanisms may contribute, including mineral transformations that release stored energy, dehydration reactions within the slab, and localized stress concentrations generated as the plate bends and sinks. Although research continues, no single explanation fully accounts for every deep earthquake observed beneath Tonga. Fortunately, the current swarm appears concentrated at much shallower depths than those extreme mantle earthquakes. Even so, every rupture provides valuable information about the stresses acting throughout the subduction system. Modern seismic networks can analyze the direction of fault movement, the orientation of rupture planes, and the redistribution of stress following each event. By combining these observations with satellite-based deformation measurements and numerical computer models, researchers gradually build a more complete picture of how the plate boundary is evolving. One of the most important lessons learned from recent decades of earthquake research is that stress does not disappear after an earthquake. Instead, every rupture transfers part of its accumulated energy into neighboring sections of the crust. Some faults experience reduced stress, making additional earthquakes temporarily less likely. Others receive increased stress, bringing them incrementally closer to failure. This process, known as Coulomb stress transfer, helps explain why earthquake sequences often migrate through space rather than remaining fixed at a single location. Whether the current Tonga swarm reflects this type of cascading stress adjustment remains under careful evaluation. The clustering of multiple magnitude 5+ earthquakes suggests that neighboring faults are interacting, but such behavior is common within highly active subduction environments. The sequence may simply represent the progressive release of accumulated strain across several closely spaced fault segments, rather than the preparation for one massive rupture. Historical records reinforce that cautious interpretation. the Tonga Kermadec margin has produced numerous earthquake swarms over the past century, many involving dozens or even hundreds of events. Only a tiny fraction ultimately culminated in great earthquakes exceeding magnitude 8. The vast majority gradually declined over time as stresses redistributed naturally throughout the plate boundary. The famous sequence during the year 2021 understandably remains fresh in scientific memory because it demonstrated that exceptionally large earthquakes can indeed emerge from periods of increasing seismic activity. That episode began with elevated earthquake rates before producing a magnitude 7.44 shock and finally the magnitude 8.1 main shock. Yet it is equally important to recognize that this sequence represents the exception rather than the rule. If every Tonga swarm progressed into a giant earthquake, the Southwest Pacific would experience catastrophic megathrust events far more frequently than historical records indicate. This distinction is crucial for both scientists and the public. Earthquake forecasting differs fundamentally from weather forecasting. Atmospheric systems evolve according to physical processes that can be directly observed across broad areas using satellites, radar, weather balloons, and surface stations. Earthquake processes, by contrast, occur miles beneath the Earth's surface, where direct observation remains impossible. Researchers must infer changing conditions using indirect measurements, such as seismic waves, ground deformation, gravity changes, and laboratory experiments on rock behavior. As a result, modern seismology excels at identifying where large earthquakes are possible and estimating their long-term probabilities. Yet it cannot determine with confidence whether today's swarm will culminate in a major earthquake tomorrow, next month, or not at all. That limitation reflects the immense complexity of natural fault systems rather than shortcomings in scientific effort. For now, the earthquake swarm south of Tonga represents an important reminder of the extraordinary forces continuously reshaping the Pacific Ocean floor. Every earthquake, whether moderate or great, forms part of the ongoing interaction between two enormous tectonic plates that have been converging for millions of years. Their relentless motion has built deep ocean trenches, towering volcanic islands, and one of Earth's most active seismic belts. As monitoring continues around the clock, scientists will be watching for any changes in earthquake frequency, depth, location, and faulting style. Those observations, not the swarm alone, will determine whether this sequence gradually fades into another routine episode of Tonga's remarkable tectonic history or evolves into something far more significant.